Good evening. Thanks for coming. We're going to get started here. We got a few announcements from the various organizations involved in this, and then we'll have our guest speaker come up shortly. Thanks for coming. We've got three organizations here: AES, BAES, and ASA. So thanks for everything, and thanks for Alvin for coordinating this for us. My name's Tony Schultz. I'm the chair of the Boston section of the Audio Engineering Society. We meet on the BC campus usually with our meetings. This is a larger room than we usually have, but it's great to have more people than normal. All right, now I'd like to call up Alvin Foster from the BAES, who was actually the one that kind of helped coordinate this, and he'd like to introduce our guest speaker.
Okay, I guess I've known Don Keele for a few years, and I think I've told a few of you, I think you're looking at the future loudspeaker over there. It won't replace, of course, the traditional two-way, three-led loudspeaker box, but it will be in the home with those who care a lot about sound. Now, who is Don Keele? Don has worked for several companies in the area of loudspeaker R&D and measurement technology, including Electro-Voice, Klipsch, JBL, Crown, and Harman. He holds 3 patents on constant-directivity loudspeaker horns and has 4 patents pending and is a fellow of AES and a member of ASA. For 10 years, Don wrote for Audio Magazine as senior editor. That's when it was a good magazine, performing loudspeaker reviews. More recently, he worked for Harman Becker Automotive Associates, designing loudspeakers again. Currently, he is semi-retired and heads his own consulting company, DBK Associates and Labs. His passion for the last 10 years has been to promote the use of CBT transducer loudspeakers. Mr. Keele holds 2 PS degrees in EE and physics from California State Polytechnic University, an MSEE degree from Brigham Young University, where he minored in acoustics. He has presented and published over 35 technical papers on loudspeaker design and measurement methods and other related topics. Among them, the paper for which he won the AES Publication Award, Low Frequency Loudspeaker Assessment by Nearfield Sound-Pressure Measurement. He is a frequent speaker at AES section meetings and workshops. He has chaired several AES technical paper sessions, and he is a member of the AES Review Board. Mr. Keele is a past member of AES Board of Governors and is past Vice President, Central Region, USA Canada of AES. Mr. Keele received the TEF Richard Heyser Award in 2001. In 2002, he received a Scientific and Engineering Academy Award from the Academy of Motion Picture Arts and Science for work he did on cinema constant-directivity loudspeakers. Don Keele has been an ardent advocate and evangelist for the concepts for over 10 years and believes the CBT know-how can vastly improve the sound field uniformity of existing line arrays and conventional loudspeakers. Don will discuss the background and history of the CBT and will describe and discuss the measurement and simulation results of several CBT line array prototypes. He will close with several suggestions for possible CBT-based home construction projects. Floyd Toole, who most of you know, is an advocate of the CBT technology and describes it in home theater applications in his book, The Acoustics and Psychoacoustics of Loudspeakers in Rooms. CBT stands for Constant Beamwidth Transducer. It is a term originated by the U.S. military in a series of 3 unclassified Naval Research Lab ASA papers published in the late 70s and early 80s. These papers describe spherical cap underwater transducers and special frequency-independent Legionnaire shading that provide extremely uniform broadband coverage without the need for any special or complex signal processing. About 2.5 years ago, another aside about Don is that he adopted long-distance running. Don was always a devotee to exercise and good eating. However, Running until recently was not his exercise of choice. Later this month, Don and his wife are taking the ultimate runner's vacation. He and his wife are leaving January 24th for a one-week cruise of the Caribbean, where they will run mini marathons on 5 of the Caribbean islands. Mini marathons. But anyway, I'll introduce Don Keele.
Thank you, Alvin. I came out to the Audio Engineering Society convention in New York and ran across Alvin while I was there, and he thought it would be nice for me to come and give a talk here, so that's how we connected up. So he was very kind to invite me out, and I actually came out here on the train, and my wife is visiting, when my youngest boy are visiting with my oldest daughter and my 3 little grandboys in Elkhart, Indiana. So I got on the train in Elkhart. It just so happens that between Chicago and New York and Chicago and Boston, that's the main route going across the country there. So I got on at midnight on Monday in Elkhart, Indiana, which is north. It's just across the border from Michigan. And then I got here 9 o'clock the next night. So it's, but you can, one thing you can do when you take the train is you can take your Leatherman on there, you know, with your knives and everything. I mean, what good thing? There's no security. That could be a good thing or a bad thing. But you know, you can take your luggage on and put it up behind you, and there's places where there's AC outlets by, and you can run your cell phone, and set your laptop up. So it's a nice way to travel. But I have been in the loudspeaker industry for a long time, and one of my first jobs was working for a company called Electro-Voice in Buchanan, Michigan, and that was my first real engineering job. And I worked there from 72 to 76. And one job that I got, in other words, one project which I was given was developing a line of large professional constant directivity horns. Actually, the project had been started before I had gotten there, but had not been put into production. And there were certain technical problems that had to be solved. So I ended up working on those, and then subsequently ended up getting EV's patent on these large constant directivity horns. And I've got a picture of some of them here. And then from EV, I went down and worked for Paul Klipsch in Hope, Arkansas for 1 year. And he and I didn't get together long. We didn't get together too well. Didn't get along together too well. So I only spent 1 year there, and then I went to, in 77, I joined JBL in Northridge, California, and worked for them from 77 to 84. And one project, of course, I got at JBL was to develop a line of constant directivity horns that competed with my horns that I had done at EV. And so I was in the situation of trying to work around my own patent that I had done at Electro-Voice. So, I mean, there's always ways of changing minor items in the patent. And so they have a line of loudspeaker horns called biradial horns, which I worked on and subsequently got a couple of patents there also. But one thing, when I went to work for JBL in 77, there were a series of 3 papers which were published in the Acoustical Society of America describing unclassified military research by the U.S. Navy. And Alvin described this a little bit to you, but it had dealt with underwater transducers in the form of a sphere or a spherical cap made with piezo. It's for underwater use. It's for underwater transmission and reception. And I thought the technology that it looked really neat to me, and I thought there might be an application to improve constant directivity horns. But it ended up that I couldn't figure out how to do it. And I put the paper aside, and then in the late 1990s, I got the idea, well, maybe we can make some loudspeaker arrays based on this, the theory that was in these papers, which is what I've done. And I wrote a series of, I've written since 2000 a series of 5 AES papers, which I've given, one of which is published, describing these so-called CBT arrays. And there are several, I'm actually telling you in advance what are some of the stuff I'm going to talk about here, but and I'll get into that. But I approximated this spherical cap with a bunch of small transducers, and then the other significant is I applied the theory to so-called line arrays, in this case vertical line arrays, of which these are an example. And they have extremely uniform polar characteristics. I mean, it's really truly wideband constant directivity. It has a polar pattern, a three-dimensional polar pattern, which is essentially independent of frequency. It stays the same. I mean, that's an ideal. I mean, obviously, when you listen to a speaker, you don't want it to sound different over on the side than it does in the front of it, or up high or down low. And typically, it's very hard to provide a speaker, particularly in a domestic environment like a living room or something, that's so-called wideband constant directivity. They all have polar patterns and coverage patterns which change dramatically with frequency. And it's not only good just to have a uniform pattern where you sit normally, but it's important that it be uniform everywhere else, because there might be a lobe that's facing up at the ceiling or over at the wall, or if you're using this in a sound reinforcement application, you can, if you step to the side, the microphone might be positioned in one of these lobes and it's going to go into feedback. So ideally, you'd like to have the polar pattern to be pretty constant. Now, the other thing I'm going to caution you with, what I'm going to be telling you and talking about today is subject of 2 patents, of which one of them I have in my name, and then a second patent, which was but applied for in approximately 2005, has my name on it, and there's an engineer at JBL whose name is Doug Button, and his idea of the so-called ground plane versions of these, where you take an array and cut it in half and put it down on the floor, which is what these are. And it essentially eliminates any destructive ground bounce. A typical speaker, if you put it in a room like this, there's a bounce off the floor. And it depends upon how far you're away from it, depending on how it causes interfering dips and peaks in the response. So these 2 patents are, I talked to the Harman's patent attorney, who I was friends with. He works for a law firm in Indianapolis, and there is these 2 patents are soon to issue, he says. So so that I have to, I'm in the situation here of actually, I might be revealing information or encouraging you to build something that may be patented, which probably is. But everything that I'm going to describe to you tonight, I've written about in AES papers, so there's really no secrets here. So feel free to interrupt me if you have any questions, and just raise your hand. And it's better to deal with the questions, at the time it comes up. Alvin mentioned that I'm a runner. So any of you do any running? Are you? Good for you guys. As he said, I just took this up about 2.5 years ago, and I mean, I really like it. I mean, I'm really a fanatic about it, just about. My wife thinks I'm crazy, so it's
That's nothing new.
And last year I've done 28 competitive events. It's mostly, I belong, in Bloomington there is called the Indiana Running Company, and they have a a marathon training group which trains on Mondays and Thursdays, so I participate in that. I'm not an official member, but it just allows me a place to do my running, and it's primarily on the campus of Indiana University, which is a big thing in Bloomington, Indiana. But I've done one triathlon. That was interesting. I can't swim very fast, so I was the dead last in the swimming, but I can do pretty good running and bike riding. And I've also done called the One America building, which is the tallest building in Indianapolis, and they had a 38 floor steps. Yes, you go and start at the bottom and go up to the top, 38 floors. Well, I got up to the 10th floor and I said, maybe this is not such a good idea. But I made it in about 9 minutes, so it was. Whereas the young guys were doing it in like 3.5 minutes. I mean, and they were going so fast that once they got up to the top, they would just flop right down on the floor. I mean, they were just exhausted. Yeah, well, I didn't collapse up there, but it was I made it. When I was out in California back in September, I was looking for some races to run, and in the mountains behind San Bernardino is called Big Bear Lake. And so there's a couple pictures of me running. I picked up the sign that they normally have on the floor, and a half marathon is 13 miles. So if you've never run 2.5 hours straight, it's quite an experience because you get thoroughly fatigued. I mean, absolutely thoroughly.
Sounds terrible.
Yeah.
Who was chasing you down?
But this is Big Bear Lake. It shows we started over here and ran all the way around the lake. They also had a full marathon and they ran around twice. I didn't do that. And I actually took the pictures along the way with my iPhone, so it took a little longer than ran it in 2 hours and 50 minutes, if I'm not mistaken. So it was pretty. This is an alternate title for what I'm going to talk about. I mean, broadband constant directivity. It's magic. I mean, it's kind of like the holy grail of loudspeakers. You do not want the coverage pattern, the polar pattern of your radiating device to change as a function of frequency. What I'm going to do now is throw up a series of systems and see if you can guess whether they're broadband constant directivity. Does anybody remember this system? It's the Infinity IRS Beta. It stands for Infinity Reference System. Not constant. Okay, no, for sure, no.
Go to the head of the class, though.
No. Now there's one. Let me see. No. I mean, in this situation, of course, in the woofer's range, it's pretty much omnidirectional, depending upon how high you take the woofer, and then it starts narrowing down. And then typically right at crossover, it'll whiten back out again. And then the tweeter itself. Now this it appears to have like a waveguide around the tweeter, and in an attempt to make the polar pattern more uniform in the tweeter's range. It probably worked pretty good.
What is that? What make is that?
Yamaha. I don't know that's not one of the NS, anybody recognize that? I just got it on the internet. Yeah, nope on that one. Well, here's just a typical three-way system. This is also Yamaha.
Nope.
No. Nope on that one. Here's a JBL product with an iPod in it. As far as I know, it has a lot of, a number of small drivers around the.
Just 4.
Is it? I don't know. It has 4. Okay.
2 on each side.
Okay. It is a nice system, though. I mean, it's. Meaning that it's convenient to use and it looks really has some pizzazz. Now here's a pro product, a two-way. It appears to be like a two-way 12-inch Yamaha system with some kind of a constant directivity horn on the top, and it's sort of in the horn's range. And if you, ideally, you can design it so that the horn's horizontal dispersion sort of matches the woofer at the crossover, so that there's no sudden transition in the polar pattern. Here's another. This would be a big professional system hung, in an arena or stadium.
Nope.
Well, it depends. Depends upon how they've set it up.
I heard one like that in the Federal Reserve System in Boston. If you were sitting in a certain row and moved your head and forth, you'd get back and forth, you would get a very deep null. Extremely deep.
Well, it depends. I mean, there are now a number of the pro manufacturers now have speakers specific for line arrays, so that you can put them, stack them up in such a way that it has a seamless high frequency exit, more or less. So you can do a lot more than you could. And I'm sure, I don't know what these are. I'm not trying to pick on these, but this is just something I found on the internet. Just something sitting outside some guy's garage. It probably is pretty loud if you're standing in front of it. Nope on that one. I don't know anything about it, of course. Maybe I shouldn't criticize it. But now here's one thing. How about a point source?
Yes.
Well, it fits the bill. I mean, it's broadband.
If it's true point and also frequency, yeah.
Well, I mean, its pattern is independent of frequency, all the way up and down. But it's omni. And that could either be good or bad, depending upon what it has a Q of 1 or a directivity index of 0 dB. It's not directive. Same thing in all directions. So there have been a number of home systems that I'm aware of that attempt to have an omnidirectional pattern. I mean, one advantage of an omni pattern is whatever sound impedance is on the wall surfaces has the same spectral content of the direct sound. So that's an advantage of a constant directivity source. There's another one, a Neumann U87, which is a ribbon mic, and it has a figure 8 pattern.
It's not a ribbon. It's
Okay, well here, okay. See, I've got experts here. Tell us about it.
It's a dual diaphragm condenser.
Okay.
And it's not constant directivity.
Okay. Well, that's going to disagree with one of the next slide here. So, if it were a ribbon and it had a well-defined figure 8 pattern.
Well, this size, it's a 1-inch diameter. It's actually larger than 1-inch diameter. It's like 3 centimeters. And above about 4 kilohertz, it loses its directivity pattern. It becomes different.
Okay, I see.
That's also true of ribbons. Ribbons are only constant directivity in the horizontal plane, typically.
Okay, well, that's true.
Vertically, and they're not constant directivity.
What's that?
It's the inverse of a common loudspeaker.
Okay, very true. Okay, good point. So I stand corrected.
So that should be absolutely no?
Yeah, right. Well, yes.
Well, it's mostly yes.
Mostly yes. Okay, now here's a photo which was taken about 5 or 6 years ago. And it's myself and Jim Long. Jim Long is a long-time marketing guy from Electro-Voice. He worked for EV when I joined EV in '72, and he's still working for them. And I think Electro-Voice is owned by Bosch now.
Yes.
Yeah. So he works. He's semi-retired and works from his home in Baroda, Michigan. But in his living room, he has 2 EV HR9040. They were called the white horns because these are the horns that I've worked on and have patents on at Electro-Voice. And it's 40 inches wide and about 17 inches high. And it's one of the first horns that really did have pretty much uniform polar pattern. And in this case, above about 500 hertz. So this is definitely constant directivity, but it's not broadband. When I say, I define a broadband constant directivity Radiators 1, which would go down to, say, the vicinity of 150 hertz or thereabouts. And in order to make that go down that far, the horn would have to be very large, on the order of 6-8 feet or thereabouts, which is big.
Two of them in the living room would be.
Yeah, yes, one off.
That would be the living room.
When this is his living room, and his living room, he has two horn-loaded systems down here with two of the HR 9040s on either side, and you sit about 6 foot in front of these. I mean, it has an intense direct sound, no room reflections at all.
It's like listening to headphones.
Yeah, it is, very much so. Yeah, well, that's a good point.
Is he married?
No.
Not anymore.
And he drives, he has, I think, 3-watt tube amps or something, because they're very efficient. So it's fun, though. Yeah, right.
166 feet.
Now, these are the horns I worked on when I was at JBL, the Bi-Radial Pro horns. This is as they existed in 1980, roughly. And Altic Lansing had their Manta Ray Pro horns, which competed with both the EV's horns and the JBL Bi-Radials. Cliff Hendrickson was one of the, Mark Ureta were the designers on these horns while they were at Altic. Cliff went on to BAES, and of course worked here. Now he's retired from BAES, if I'm not mistaken. Anybody here from BAES tonight? Very good. Expos, okay. Somebody back here too. All right. Yeah, again, if the horns are big enough. And this is the system that my second ground plane CBT prototype, which is right over here on the side. And I have yet another one that I constructed when I was at JBL, Harman actually. I call this one the CBT 45 because it's a 45-degree arc, and this is roughly a 6-foot-high array composed of 90 tweeters and 34 2-inch drivers, which I call the CBT 30. And I essentially worked on these as an underground project or a skunkworks project. Oftentimes when you're in a corporate environment, you get an idea. You have to sell your idea inside the corporation too. And I've been trying to do this, and they haven't, with the exception of some pro products, which JBL has now. They haven't taken much advantage of it. So I'm trying to promote these things. Now today, Marshall K is here. Where are you, Marshall? Okay, there he is. There are, as a result of my papers, which I have given to the AES, they, on their own, essentially absorbed the content of the paper, and we're building basically some DIY projects. In this case, these are systems that Marshall and Monty are brothers, and this is a CBT array that's 120 degrees, which Monty has a world-class home theater system. And he was looking for a distinctive center channel to put in there. And this is distinctive, all right. And how many tweeters on this, Marshall? 132. Small Tang band. And so
It's a three-way.
yeah, it is a three-way. And you can see the row of tweeters up here, and then mids, what are those drivers? Is it
2-inch aura.
the 2-inch aura? What are these?
Those are 6-inch parts express with a truncated frame.
Okay. I'm sorry, what did you say?
What cost that we're talking about, Marshall?
I'd have to add it up. If you give me a few minutes to think about it, I could give you a number. I don't even know what it is total.
Parts Express has a number of drivers that are small and inexpensive, so it's a.
And can we come visit you?
If you go to Austin, my brother will be happy to demo the system. It's incredible. It's phenomenal sound. Best I've ever heard at any home theater anywhere.
Yeah, so I'm going to say a big yes on that one.
Question,
Yes.
that center channel speaker looks as though it was meant to be placed horizontally.
Yeah, it is, absolutely. I'm going to go into more detail on that.
Okay, because the directivity would be very different.
Of course it would be, because it's a line array, and I mean, he wanted to have extremely uniform but well-controlled horizontal coverage. And so these are oriented horizontally and not vertically. It's not a horizontal line array rather than a vertical line array.
Just wondering how it would balance in a system that also had vertical line arrays.
And his system does.
Side speakers.
Monty's system has basically
It has infinite line arrays on each side.
like floor to ceiling.
Floor to ceiling, and there's the subs are also infinite line arrays, and everything on the line array part's a dipole. So it's a dipole line array, and the subs have 12 15-inch drivers on each side.
A lot of air moving capability there.
The neighborhood lights dim and turns on.
The opening scene of Iron Man will scare you to death.
What's the purpose of the vertical line array? To cover like short and tall people? I'm trying to understand why you want to have the vertical line array so much. Then I can see.
Well, I mean, what I'm going to talk about tonight is this is a better way to do the vertical line arrays, which I'm going to make the case for it. Now, I had a discussion with Harman's patent attorney a couple of weeks ago, and of course I'm giving information out here, and I'm not encouraging you guys to go out and build these things, although you'll have to talk to your own. But there are two patents which are pending at this moment, which are going to be, one of which I did, well actually was applied for back in 2004, and then the second one was applied for in 2006. And this one specifically describes the ground plane version of this, which is what I have over here. So I'm just cautioning you. I mean, the military prior art, there's actually 4 papers that were published between, actually 3 published papers, and one was a technical report. And the most interesting one was by Rogers and Van Buren, a new approach to a constant Beamwidth transducer, which was in the Journal of the Acoustical Society. And that was 78 July. And there were a couple, another one, and then yet another one in 1983. And this is a copy of the Rogers and Van Buren paper. And as I say, this has a quote. This is from the introduction, somewhere right in this area, but it would therefore be desirable to have a broadband directional transducer whose beam pattern is essentially independent of frequency over its bandwidth. With such a constant beamwidth transducer, CBT, and that's where that came from. There it is right there. And this goes back to 1978 now. The spectral content of the acoustic signal would be independent of bearing. That's kind of formal language for them that the underwater transducer people would use. But at the time I picked up on this, I thought it might help me in designing a constant directivity horn. But it ends up that I wasn't too successful at that. So I set it aside, and then 10, 15 years later I picked it up again and thought it might be neat to design something based on loudspeakers. Now my computer stopped working here. Sorry. No, it really has. The page up and page down keys aren't working either. Oh, no, it's not even escaping. What's happening here? Okay. I don't know what I did. I just treated my ThinkPad to a 500 gig hard drive, and they upgraded it at the same time to Windows 7. So I'm learning how to make that, so that may have something to do with that. Blame it on Microsoft. I've written 5 papers. The most recent one in 2005 with Doug Button, where we described the ground plane versions of these things. And this is what the original paper that was published in the Acoustical Society of America described what's called a spherical cap. When you have a sphere with a cap on it, this is a side view, and then a kind of an oblique view, or some angle. And they describe a so-called shading function, which they apply to the surface of it actually describes the velocity distribution as a function of angle. And it's at the center of this spherical cap, its maximum, and then it tapers down as you get off from the center, following a so-called Legendre function, which is one of the orthogonal. And they discovered that if you track this Legendre function down to the first zero crossing, it looks kind of like a sine x or a sine x over x or a sinc function that oscillates as you go down. That's what the Legendre function does, the same thing. And they found that if you apply this shading, and this is somewhat, some of you are, of course, experienced with FFTs, and you have windows which are applied, a Hahn window and a Hamming window and a Bessel window. It does the same thing. This is kind of a shading that's optimized for sources around an arc or a circle or a surface of a sphere that works the same way. It reduces off-axis lobes. And this is these are some of the shading functions specifically for actually a 10 degree, 15 degree, and a 20 degree shaded cap. And in my first paper, I came up with a series approximation of that. And here's the other thing. What they're claiming is that if you have the velocity distribution on the surface of this spherical cap, if you look at what happens in the far field, the pressure actually the near field and the far field essentially follows the same function. So they say, and therefore the surface pressure distribution, the near field pressure pattern, and the far field pressure pattern are all essentially the same. This is their wording, i.e., there's no near field, which is, meaning a near field. The concept of a near field on an acoustic radiator, you get beyond a certain point of a radiator, and the polar pattern more or less settles down. But as you get closer to it, there's interferences, and it changes when you get up close to it. But this doesn't. And that's.
How is the shading applied? How was the shading applied?
Well, in the original military, I'm not sure exactly, but it was all done with piezo. These are underwater transducers, and
it's a hemisphere.
Yeah.
And
Yeah. Well, a spherical cap, so it could be a hemisphere.
That's what I was wondering so as you got closer to the edge where it was.
It tapers off. Now, I do not know how they actually got the amplitude distribution, or the amplitude to decrease as it goes off axis. But I know how I did it in the speakers, of course. You just simply turn them down, by whatever means. Now, I came up with just a simple, actually a 4-term power series, which approximates the Legendre function, and that's up here. And it shows, this is the shading level as a function of angular. And this would be the center of the array, and that's the outside of the array, and both in linear and logarithmic. And it's down about 6 dB at 64%. So this is an approximation to the Legendre function. This is easier to implement, which tells you how to apply the shading to the transducer to get these magic qualities. Now this is out of one of the fourth paper, but they were illustrating how the shading changes as a function of angle. It's maximum here, and the length of these vectors tapers off to essentially nothing at the outside. And that illustrates how the shading is applied. Now these are also out of those papers, but they talked about several different radiators. Well, actually, here's the angles down here. It's 13 degrees, 17, and 25 degrees. And they plotted the polar patterns as a function of frequency and then did an overlay of them. That's all very uniform, and it fits in a very tight pattern over a wide range. And of course, similar to a large constant directivity horn, there is a low frequency limit down to which the beam width is controlled. And as you get down to where the wavelengths are larger than the radiator, it doesn't control anything anymore. So these things all have to be relatively large with respect to wavelength over its whole operating range.
Question?
Yes?
I presume there's also a high frequency limit which depends on the spacing.
Absolutely, yes. Yeah, that's when you end up with loudspeakers, that's another thing you always have to. It's roughly that frequency where the spacing is a half a wavelength or thereabouts. Now this is basically covered in my first paper that I published in 2000, but was trying to approximate a spherical cap with an array of loudspeakers. A whole bunch of loudspeakers, obviously. The smaller the better. And the smaller they are, the more there are. And I also, because that radiator has a symmetric pattern. It's axially symmetric. So I considered a so-called an elliptical toroidal cap. I mean, a toroid or a donut has two radiuses of curvature. So this allows you you can have this would, as an example, would be a radiator that would be, might be 90 degrees horizontal and 45 degrees vertical, as an example. Then the most interesting one is a circular arc line array, which is an example of which is sitting over here. And basically what you do is you arrange your speakers around a circular arc and apply this frequency-independent Legendre shading. And I have some simulations that I'm going to show you where I just simply took a 100-degree circular arc, and that's about one wavelength, and the height is about one wavelength at 1 kilohertz. And I simulated it both with and without shading. And note that because this is frequency independent, you can often do the shading passively. I mean, by network manipulations and everything, because the shading is just simply turning the volume of the speaker up and down. Changing the level. Here's an example of that same array without any shading. They're all on at 0 dB, top to bottom. And then this is what it looks like with shading. And one thing that I'll talk briefly about is I came up with an approximation of the shading, which basically truncates the shading at the minus 12 dB down point, and then furthermore does it in steps. In fact, in this case, it was minus 3 dB steps. So that simplifies it, trying to implement this. And again, these arrays on axis is this way, and it's symmetrical up and down. This is an example. This is actually the shading schematic from that speaker that I have over here. And there are actually 5 banks, 0, -3, 6, 9, and 12. And the shading is done, the first three banks are done with a series parallel. This one divides it by 2, which is 6 dB, and this divides it by 3, which is another about 9.5 dB, which is 3 dB difference. And then this one divides it by 1/4, which is -12. So there's by 0, -3, -12. I'm sorry, 0, -3, -6. And then these were done with resistor attenuation networks. Now this is covered by Harman's, the first patent that may issue here pretty soon, this networking. So they're going to have some patent claims on that. Now this describes what I was doing. The full shading actually goes down to 0 at the outside edge. This is in dB. But I came up with, you can truncate it at the -12 dB down point and then have steps in between. So this shows you the steps. So that's just a way of approximating it. It's still best if the shading were continuous and changed with each speaker going off. This is an example of a curved line source without shading. Now this is the so-called beamwidth. I mean, that's the red is the vertical beamwidth, and the blue, which is going across the top, is the horizontal. So I mean, of course, beamwidth, to you pro sound people, that's the angle, the included angle between the 6 dB down points and the polar pattern. And so ideally, a beamwidth that was constant with frequency is ideal. And also the so-called directivity, which describes how the energy is radiated. In order for it to be constant, again, this would be a situation where this should be a nice horizontal line. Now here's something which I call the on-axis loss as a power loss. Anytime you have speakers arranged on an arc from an observer out in the front, the outside drivers are farther away from the observer. And as you go up in frequency, they become, the contribution from these outside drivers becomes more and more out of phase because it's a curved arc. And so it ends up that over the whole range of a curved arc speaker, it roughly rolls off at -3 dB per octave. And that's just a result of it being curved. Now you don't necessarily have to curve it, you can make it straight. In which case the on-axis loss is nothing because you're always on axis. I mean, they're always aimed at you. I don't know if that made any sense, but now here's, as soon as you apply the full Legendre shading, this is without and that's with. It's a big improvement. I mean, it makes it constant over a very wide range, the beamwidth. The directivity is also quite constant. And this on-axis loss rolls off very well behaved.
Excuse me, I'm not sure how do you find directivity in this case?
Well, I mean, I deliberately didn't get into that, but I mean, it's a comparison. I mean, directivity or Q is important for radio frequency antennas also. It's the gain that you get. I mean, you take two sources, an omnidirectional source and the source that you want to evaluate, and you go in a prescribed direction, and you compare the sound pressure that you get from the directional source versus the omnidirectional source. And I mean, obviously, if you have a directional pattern, I mean, a pattern which is directional, you're going to, and you radiate the same amount of energy, it's going to concentrate it more, and it's going to be more in a certain direction. So it's a...
Is it simply a function of beamwidth?
Yeah, well, no, it's a function of it's the three-dimensional pattern, actually. But it's because it's defined in a specific direction, it changes depending on where are you.
Defined on axis.
Usually it's on axis because that's the point that has the highest sound pressure usually.
Don, an important point is you compare the directional speaker to the
Yes.
speaker for equal total radiated power.
Yes.
That's the important point.
That's correct. That is exactly right.
Radiated power. So the directional speaker is going to have a higher
Yes,
sound
yes.
pressure level on axis than the omnidirectional.
Right, that's absolutely true. And you can have a directivity of 2, which ends up being a directivity index of 3 dB, goes up as 10 log. Or if you have a 6 dB gain on axis, that would be a Q of 4, and that's 6 dB. But if it has a radiation pattern, which is the same with frequency, it's pretty much the Q, the directivity, well, in this case, the directivity index is over here in dB, and the directivity factor is over here. So this is pretty darn near perfect. So it's surprising how it changes from here to here just by applying this shading. So it's kind of optimum in terms of drivers around an arc. Now there are two versions of the ground plane, two versions of a line array that you can have. One is a so-called freestanding version, which is symmetrical up and down. Now you can also, you have the luxury of basically cutting the bottom half off and lowering it down on a reflective surface. I mean, that's like the police cars that used to have the dipole antennas sticking up on the top, and those were all ground plane. It depended upon the ground plane reinforcement of the top of the police car, and therefore it operates better. It's yes.
Then you could conceivably also have a 90-degree array that slopes all the way back to the rear wall.
Absolutely. I mean, that would have a 180-degree arc.
Yes.
Yes, that works as well.
Actually, if it hit the floor too, you'd have a 360-degree arc.
That's true. Yeah. Yeah. We don't know. So here is where you actually cut the bottom off. But this actually, if you think of an array, if you make this height the same as that height, you notice that the portion of the array that's down here, you've actually doubled the height of the array. And that's real convenient for a home application. On these two systems, the left speaker has a mirror down on the floor, and you can walk over there and look down and see the part of the array that's down below ground level. So it doubles it. So I mean, really, that's about a 4.5-foot high array, and so the total array that you're actually listening to is like 9 feet. It's a big array. If you take your real-time analyzer microphone and put it down on the carpet, it suffers a high frequency loss due to the grazing. So it ends up that from a practical standpoint, the carpet doesn't make a whole lot of difference. The carpeting works quite well, or it doesn't work. Typically, a speaker that you've set on the floor of your living room, there are certain wavelengths and paths where you end up with a direct sound and the bounce off the floor, and they may end up in phase or out, in phase or out of phase, or in polarity, out of polarity. It causes a series of cone filtering effects because of that. So in this particular instance, you still, even though this kind of carpet is fairly benign. It's not too. It doesn't upset the concept of this ground plane. It seems to work well anyways.
Most carpets are actually not as absorbent.
That's true. Okay.
Even a fairly flush carpet.
You get in talking about reflection coefficients and things like that, and I would expect a hard surface covered with a piece of carpet. Its reflection coefficient is fairly high at most frequencies. It's not absorbing much, right? Yeah.
It's especially true once it gets worn.
Yes,
people always want to use carpets at restaurants for noise control. The problem is it might be reflective when it's new, but once you start walking on it for a while, you start patting it down.
It stops absorbing. Yeah. But what I found from a practical standpoint is basically if you listen to these speakers lying down on the floor with your ear near the floor, you're going to have some high frequency loss. But for the most part, it's not too important.
If you're listening lying down, you probably, if you're on the floor.
Who's talking? Oh.
If you're on the floor listening high frequency
That's true. Well, that's one thing. When I have these playing, go over there and put your head down near the floor. I mean, it doesn't change much. Of course, that's also true of the so-called infinite line. I mean, if you have a straight line that goes that sets on the floor and goes up to the ceiling, you know, it doesn't make a whole lot of difference where you're listening to it because you're always essentially on axis.
I wonder how your neighbors, if you're an apartment dweller, likes the loudspeaker sticking out through their ceiling.
Okay. I mean, that's the business about it. Imagine the floor being a mirror and the ceiling being a mirror. And you put this array there, you can see it go off to infinity, either both ways. But true line arrays have problems of their own. I mean, they're, if I'm not mistaken, they're dispersive. I mean, it doesn't preserve wave shapes very well because it.
Right. Path length is different for all different frequencies.
Okay, I'm having difficulty with this. Yes.
Well, also.
I mean, it's not one of those. It rolls off at 3 dB per doubling of distance. But it's not good. It's not like a point source, and it's not like a cylindrical source. It's a no matter what it would be.
Well, a line array will get very lowly as the frequency goes up.
Yeah, well, not necessarily for an infinite line array, but I know a finite line array. I was going to cover that here.
Well,
Yeah, that's one thing. What I did was I did some simulations of 6 different line arrays. And I'm going to share that with you now. I did a straight line array without shading, and I did a straight line array with shading. In this case, I'd used a hand window or hand shading, and I did 2 curved arc line arrays, a 60-degree circular arc without shading, a circular arc with shading, which is actually a CBT array, and I did a straight line array, but it's delayed. The arc is created by delays in the processing.
These are vertical?
These are vertical arrays, just like these.
So the angle they're looking at is the vertical?
Yes, indeed. I mean, these kinds of arrays, assuming that depending upon the sources that you use, are essentially omnidirectional horizontal. But the control we're talking about, this is the vertical plane sound field. And I also did, because in pro sound use, they have an array, which you might call a J array. Typically in a big sound reinforcement situation, they put up a straight line array, which is very directional. They aim towards the rear of the audience, and then of course the front of the audience doesn't get covered too well, so they put a circular arc array underneath it. So so it looks like that so I analyzed that also. It ends up that has somewhat the problems of both the unshaded circular arc and also the problems of now this is just a depiction of those arrays. The first one was a straight line 2-meter high array, unshaded, and then one that was shaded. Now note here the level, it's 0 dB in the center, and it tapers off down to the ends. 0 dB minus 1.4617. That follows a so-called hand window or a hand shading. And then I did an unshaded circular arc and a shaded circular arc following this Legendre. This is actually a CBT. It's 6 dB down. So roughly, it's actually 3 dB down out to about this far. So it has most of the drivers, like 2/3 of the drivers, are either on full or 3 dB down. Now this is one which is curved. It's a straight line array, but curved with signal delays. This is quite complicated because you have to have microsecond accurate delays for each of these little bitty speakers, which means you have to have amplifiers for them all. If you can put them around an arc, it works a lot better, but you don't have to do that. And the last one is a J array, and this happens to be a 1 meter high straight array with a 1 1 meter high circular arc down below. And there's a number of conditions. All of these, I had the center of the arc at the origin. I'm going to go through this real quick. Now, what I did is plotted the sound field, the vertical field, over a region which is roughly 6 by 6 meters high and deep. And I did it at 1/3 octave centers. And I actually equalized all the arrays flat at 6 meters away. And this is an example of what you're going to see. On the left is a sound field plot. I hit the wrong button there. Now we're going to have to go back. Yes, I know. Pardon me while I recover from my error here. Here, there's a button down at the bottom of my remote that turns it on, and that's what I didn't try to hit first. Okay, I'm going to switch over to. I gotta move on here. Now what I'm going to show you is that whole series of sound field simulations at 1/3 octave centers going from 50 hertz up to 20 kilohertz. And again, what you'll notice is that, this is a magnitude scale with the yellow hot, and it goes through red to black. This is essentially up 10 dB, and that's down 40 at black. And this is, you can see the actual array over here, where all the point sources are equally illuminated. Now this is magnitude and this is phase, so that's a constant phase contour. And as I skip up in frequency, that's one wavelength between here and here. That happens to be 100 hertz. So as you see, as I get up higher and higher in frequency, you can see the wave shapes basically. Let me go quickly here. Now look at what happens over on this side. You can see the lobes which occur. You see the lobing? And notice what's happening over here. The constant phase waveforms are pretty much straight here, and then they curve around to the side. You kind of expect that. It's not a point source. But as I go up, you can see the frequency up on the top here. But it's not very even. Now there's spatial aliasing going on here because there's not enough sample points to show the phase changing rapidly, but you can see it's essentially straight in front. But now look over on this side as I go up and down, and particularly look at the near field. Look at it changing. There's a lot of detail in here up close to the array, and that's a problem with just straight, the so-called infinite lines. And then there is a frequency where the spacing of the sources is roughly a half a wavelength, and you start ending up with grating lobes or end fire lobes. See what they look like?
Would that be
way planar magnetic works.
No, it wouldn't have that at all. It's continuous. It wouldn't have that problem. It would still have this, you know, so there. So that's not, if you have your, this means that, if I'm not mistaken, this has, it says 100 sources, and the sources are spaced at like a half an inch or so. So you wouldn't normally operate it up this high, because it has a big beam going down and up. But you can see it has a real rich pattern. And this is a finite line array. Okay, now I'm going to switch back. Now what I'm going to show you, I have, why is that feeding back? I thought I shut that mic off. I've made a composite slideshow that I'm going to show kind of in a movie mode, which shows all 6 arrays. This is the straight line, no shading, straight line with shading. The lower left is the curved line array, no shading. This is a curved line array that's with shading. That's what I call a CBT. And this is the delay curve straight line array, and this is the J array. Now this happens to be at 1 kilohertz, but you can see the patterns. This one is quite well behaved in comparison to that one, but it gets, the directivity of a line array continually rises because it gets narrower and narrower as you go up in frequency. But this is a lot more the one over here is a lot more well behaved than that one. And this is a curved line array without shading. Now these two are the CBT arrays, and it has a well-defined coverage pattern. And this is the J array, which is kind of a combination of the straight line array plus this one hanging below. Now I'm going to run this in a movie mode so you can look at it cycle through. And these are simulations. You can see the frequency up in that cycling from 50 all the way up to 20 kilohertz. Now this is exactly what I showed you before, complete with the grading lobes, the upper left. Now this is a lot more well behaved, and you don't have those off-axis lobes. But it continually gets narrower and narrower as you go up in frequency. Now this one also doesn't work all that well. This is the curved array, no shading, and it has a lot of lobes, and particularly detail right in the up near the arc. But now look at these two now. These two are the CBT ones, and as you get up beyond about 500 hertz, they radiate with a well-described angular coverage. And the pattern doesn't change hardly at all. You see, it just looks like a, and that's the advantage of this. Now the J line array, yes.
What shading is on number 2? Is that genre shading?
No, hand weighting, a hand window, and that's just like, you know, a cosine squared, 1 minus the cosine over whatever it is. I've forgotten. This is a much more severe. I mean, it cuts off the outside much quicker than the Legendre shading. So these two are so uniform, and all you're doing is putting the drivers around an arc and applying the shading. Now this is done with delays though, so you can actually see it straight. I eliminated one, not eliminated one slide. I was just pointing out that the CBT. These are the CBT arrays over on this side, and I did that. One claim that is made of these CBT arrays is the fact that its polar pattern is independent of distance. Now, how can that be? That's because the velocity shading at the surface of the array is essentially equal to what it is in the far field. So in this case, I've illustrated a very high, like a 14.5-foot array, and this happens to be a 48-degree arc angle, and its center of curvature is over here, something on the order of 212 inches. And here's a microphone 1 meter away from the surface of it. And you're rotating this whole contraption around that point right there. And this is where these are so-called polar maps. This is frequency along here. This is angle, and then the sound pressure, in this yellow hot. So it indicates this is run at 100 meters, 10 meters, and 1 meter. And this essentially, they're all the same essentially, except when you rotate this thing around, of course, and when you're close, there's a dramatic difference between where the drivers are when it's faced towards the mic and when they're not, so that corresponds to the differences down at the bottom. I'm now going to talk about some of the trade-offs and design aids for these arrays, and I have some design nomographs which I came up with on my own to help me design these, and I'm going to talk about some of my prototypes and some of the drivers that you could possibly use to implement these, and some of particularly the pro manufacturers have speakers which you can use that could be utilized to form these. And Marshall, who is sitting here at the front, he read a number of my papers and created a CBT, or series of CBT arrays for his church in Raleigh, North Carolina. And he did this pretty much independent of me. I mean, he, just from what I taught in my AES papers. And I'm going to show some pictures of that. And also Monty Kay's home theater system, which I showed briefly. These are a couple of nomographs which show the variation of the height of the system along the bottom axis, the angular coverage, and the low frequency limit down to which the beam width is controlled. And it's the formula, the behavior of these things is very much like a big constant directivity horn, i.e. if you want a wide angle high frequency device, it can be small, but if you want down to a not such a low frequency, or if you have a long throw horn that you want to control, say a narrow 10 degree down to say 100 hertz, it's going to be gigantic. So this just shows the trade-offs. There's one particular place here was a design, and then also there's a corresponding one for the ground plane versions of the same thing. And then you can see all the curves shift down. This is quite thrifty because you're actually creating half of the array due to the reflection of the floor. Yes? Oh, I'm sorry. Thank you. I'm going to do it here on the computer.
While you're doing that, can I ask?
Yes, I thank you. Thanks for pointing that out.
Would this technology also be very applicable to microphones? Would there be an advantage in using it in a microphone?
Well, it potentially could be, but you have in a microphone you don't necessarily have to have high efficiency because you can do it with gain externally. I mean, so you oftentimes in microphone designs you can get your polar pattern, by putting two sources close together out of polarity to get some kind of and its low frequency response rolls off like crazy, but you can equalize it easy. There's a hand over here.
John Erkel's microphone book does upper line source microphone.
Okay, that's good. Okay, that's a very good source. Yeah.
And in particular, it showed a lot of graphs that are similar to yours about the 3dB rocket roll-off.
Okay, good, very good. I haven't looked at his book in quite a while. Now passed away, of course. I mean, they're so-called in-fire mic. You know, the shotgun microphones can be classified as an in-fire. I mean, you have sources or receptors along a line, and you have it aimed at you. Not like we do with speakers, but like this.
But in your graph, I'm having pointing at those beams that were shooting out.
Oh, okay. That would be the same thing. Yeah. Good point.
I would say this. I've never had the opportunity to take a decent course in acoustics, but I did take a course in antenna theory, and a lot of the same theory applies.
Absolutely, I agree. Yeah.
Whether it's a transmitting antenna or a receiving antenna,
Yes.
the symmetry that's inherent in the mathematics about that. And I would think that would also apply to microphone arrays.
Absolutely. But the disadvantage of doing this as a microphone array would be that it would be large. I mean, you might end up with a 2-meter high line array. It would be I mean, you can carry, that's true. So that's a...
It was supposed to be particularly good for picking up large areas, so that's what the microphone...
Well, I mean, you would end up with a microphone with an extremely good polar pattern. Yeah.
I've thought a lot about that for miking singers and operas, but I've never actually implemented it. Lots of people have said, "Oh, that's a great idea," but nobody said, "Here, make it."
Yes.
Dr. West of Sound Lab, who makes very large electrostatic speakers, has actually built I think it was a 9-foot semi-cylindrical electrostat and used it as a microphone.
Okay. But it was a circular arc, do you think, or what was its shape?
This is semi-cylinder. You take a section of a cylinder.
Okay.
And it's implemented.
I mean, here's a cylinder. You mean take a
vertical section.
Okay. Well, somewhat like your speakers over here, actually.
In a way, yes.
Who was that? Who did that?
Dr. West of Sound Lab, who's a physicist, has been building electrostatic speakers for quite some time, and use it as a microphone.
Parts Express and Matasound are two companies that, I mean, if you're an audiophile, a loudspeaker do-it-yourselfer, these are great catalogs to look through. And they have a number of Parts Express particularly, and also Matasound. And this is a driver which potentially has some application. It's a 2.25-2-inch full range basically. But the most important part is in quantity. It only costs $2. So I've got some samples of this up here that you can come up and look at. And of course there are small tweeters. Now with the advent of laptop computers and cell phones, there's a lot of little bitty speakers that you can find there. This is happens to be one company called Regal Electronics, and they're so-called micro speakers, and all of these are mostly less than a 1/2 inch in diameter, and they're wide band. I mean, you can use them over 600 to 20 kilohertz, say, little bitty guys. And then they have some other ones which I haven't shown here. They're in the range of 12 millimeters up to 25 millimeters, or 1/2 inch up to 1 inch. I haven't tried any of these, but there's certainly possibilities. In my second AES paper, the third one, I used Harman multimedia drivers, and these drivers are 2.25 inch, called the Odyssey 7, and it was used in the original Apple iMac. Remember the iMac that sat down and had 2 speakers here? That was the driver that was in it over here. And this is called the Odyssey 2, and it's used in both, or used to be, in the Toshiba and Dell laptop computers. I mean, basically it's a 1/2 inch inverted dome wideband speaker that you can actually use down to 400 hertz. And I've got a sample of that here. And I built my third CBT prototype was built with this as the. I mean, you can do this. This is like a tweeter subwoofer.
Just order them as spare parts from Toshiba or Dell. Where'd you get? How did you get them?
Well, I mean, Harman Multimedia makes these for those companies, and so I.
So how do you just? I mean, how would somebody get them? How would somebody distribute them?
I don't know what the situation is now. I don't know, whether. I mean, they're obviously made over in China somewhere, But again, this is all, potentially patented or soon to be. But the advantage of this is basically it looks like a little half-inch tweeter. Has good flat response, but you can cross it over like 800 hertz if you want, which is unheard of. I built a number of prototypes while I was at Harman, and one of which is this. Let me skip in here. This describes all my prototypes. These are PowerPoint that I did like posters, and they're all afterwards. If you want to go over here, they're all posted up on the wall. Look over here. So you can go over and gaze at them. This was the first prototype I built, this one right here, which actually used 18 of these Apple iMac drivers, from roughly 100 hertz on up to, in this case, I think I crossed it over at 1 kilohertz, and that it uses 50 of these little small drivers that I showed you, and this is 1 meter high. This would be qualified as a freestanding CBT. And then the second prototype I built was the one that you see over here now. It's a 45-degree arc. Now I'm going to go into a little detail later on that. And the third one I built was a floor-standing ground plane using 90 of those little tweeters. A bunch of them, lots of wiring. You can see some of that here. I also actually built a version using automotive transducers because I was working at Harman Becker at the time. I just put this in as a kicker. Do any of you remember the Harman Kardon sound sticks? I mean, they're 2 little clear plastic with 4 little mini drivers with look like a spherical shape clear plastic with a woofer that's facing down. And that's where I got the idea. I thought it would be neat. I went out and found some clear PVC pipe, and that's why those look like they look, for whatever that's worth.
Question?
Yes.
How did you get the PVC pipe that was bent, or did you bend it yourself?
That's a problem. I actually called the company that makes this clear. I mean, this is the same stuff as you route your toilet in your house underneath, PVC.
Yeah.
But this is piping made for the medical industry primarily. That's clear because they want to see what's going through it. And I talked to the Horvel, I think Horvel company, and they said that it would be possible to bend that. Now these are not bent. These are composed of 8, divided up into 8 sections, 45 divided by 8. And they're 8 straight sections. And there are, if I'm not mistaken, there are 6 drivers per straight section. So it's an approximation of an arc. The approximation is pretty good, however. I mean, if you divide a 45-degree arc into 8 different sections, the error is not much. Now this is actually, these are the systems you see over here. Now it's a 45-degree arc, it's a ground plane design. It's about 54 inches high, 1.3 meters. I mean, it's about this high. You can see them over there. And it uses, one of the Harman companies is AKG, when they manufacture some very fine headphones. And this uses 48 of the AKG, they're called XXL V5 headphone drivers. And I have a sample of that up here too. If you're welcome to come up here and take a look at them. It has a fair amount of excursion, and it has most importantly, it has 120 hertz resonance. I mean, which is for a driver this size, that's low. And so and I used 48 of these, and I thought it would be nice because it doesn't require a crossover. I mean, there's no other than the shading. That's basically a one-way system. And these are crossed over at 150 hertz to the sub by near the back wall. I also have some other driver samples up here which you can look at. And this roughly has an operating range down to 100 hertz. But I mean, this is not a rock and roll system. I mean, it still plays adequately loud. And it's surprising how many how loud 48 headphone transducers will go. Yeah, 5.625 degree. Yeah, 4-inch clear PV sight, and Harvell Plastics is the name of the company that provides that. And that has at the 6 dB down point, these arrays have a 34 degree vertical beam width. On the ground plane, of course. Or above the ground plane.
It's 34 above, so it would be twice that in
below, absolutely, yes. So I mean, as I say, there are mirrors over there. You can walk over and you can look down at the ground with the mirror, and you can see what you're listening to. I mean, in effect, you've got a room that's twice the height of this room, with the array dead set in the center, and you're walking along this, the midpoint of this room that's twice as high. And this controls its coverage down to raw 200 hertz, so it definitely qualifies as a broadband constant directivity radiator. And these are just some line drawings of this one. These are some tests we made on it. This happened to be in our lab, and I was running some curves with the microphone actually on the floor over at 10 or 15 degrees off axis. Here's a picture of me standing next to one. Another shot. This is I actually showed this again, but it shows the method by which the shading was accomplished. And it's all passive. Again, it's stepped and truncated Legendre shading. And again, it's 0, -3, -6, 9, and 12. And these are the ones over on this end are done with a resistive voltage divider. If you go over and look at these, there's a little PC board down at the bottom that all the drivers connect up to. And if you look on the back, you can see the little surface mount resistors. But if you look at, I calculated the maximum powers here, and it's only on the order of 1 or 2 watts, so it doesn't require a whole lot.
Question?
Yes.
What is the impedance of the drivers, and what is the impedance of the entire system?
Okay, those are coming up. The best thing to do this scheme with is a high Z. These are 48 ohms. High Z. So it's nice because you can put them in these massively parallel series arrangements and not get the impedance way down. So that's an advantage. Now here is if you were to turn those down sideways, it shows the levels. It's 0 dB out this far, -3 out here. So roughly 2/3 of the drivers are within 0 to -3 dB. And then it's -6, 9, and 12 out at the outside end. Now here is if you look at that schematic and you plot the voltage drive to each individual speaker, one of which is in each bank, then you get this. And you can see they're roughly all, with reference to the first bank, these are roughly all 3 dB down. And then there's variations around the resonant frequencies of the drivers, as you'd expect. But it's not bad. Now this is the most interesting thing at all, and if you take the specific AKG headphone transducer, and you measure its so-called half-space frequency response like you would a normal speaker, lo and behold, the response rises at 3 dB per octave from roughly 200 hertz up to 10 kilohertz. Now the other question is, if somebody asked me to design a driver to do that, I have no idea how you'd do that. It just so happens that that 3 dB per octave rising response just compensates for the power roll-off of the array. Yes?
What sort of baffle is that? Is it just the driver hanging out?
Oh, no. This was in a... Actually, what I did is I took 6 of these drivers and mounted it in that cylindrical, it was about this big, and I actually measured it with the drivers mounted in a closed box, the same shape as that. Yeah, well, these are just some different, I measured it at 1/4 of a meter, 1 meter. I measured in the near field because I could get some good low frequency and then made a composite out of it. But when we had the real time going earlier, it's surprisingly flat. It doesn't change hardly at all, with position. It's just more or less an accident. Because if you use a normal driver like the ones on the table, this one specifically, those are all flat in the half space. And you put them here, it exhibits that 3 dB per octave roll-off, and you have to equalize that. But this kind of self-equalizes.
Is that showing a resonance around 2K? Is that in the piston band at little in the near field response? There's
Good question. I think when I originally designed these, I had each one tuned with a duct in the back, and it was tuned to somewhere around 120. But it had an extremely bad organ pipe resonance up around that frequency. And I think when I measured these, that was vented.
So that's a consequence of the port, not the...
Yeah, that's yes. Yeah, no. That's a good point, though. I think that's where that... the resonance, the Q was rather high. You could hear it sing, particularly if you went around the back of the speaker. So I just took them out and covered the hole up with duct tape. Now, here's getting back to your question. This is what the system impedance looks like. And this is with it vented, and I had it tuned to 120. I've since taken that out of there, so it's just a simple peak. So, in terms of a domestic system, this is very well behaved. Now, this is my third prototype, which, I'm sorry. Yes, somebody asked a question? No? Okay. This is the third prototype I constructed called the CBT-30. And it uses, it's roughly 6.5 feet high, 30-degree arc. And it uses 90 Odyssey 2s, the little driver, and uses 34 of the Warrior drivers, which I have a sample of up here. These are all Harman multimedia drivers. And again, over on this side, it shows the approximate shading from the floor to the ceiling. And this is crossed over rather low. Physically, this is only about that wide. And I crossed over the tweeters versus the mids, or whatever you want to call them, at about 1 kilohertz. So it's omni-horizontal for sure.
What order of crossover is that?
I think this I did process, so I think it's a 24 dB per octave link with Riley. But I also designed a passive crossover, which was 12 dB. But I didn't end up constructing that.
Question?
Yes.
You say omni-horizontal, but as you get farther and farther from the axis, it's going to look more and more like a straight line array. That is, it'll be curved.
Indeed it is. Yeah, I didn't mention anything about that. Yeah, there's a peculiarity of these curved arcs that the vertical coverage is a function of the horizontal axis angle, and it does this. But it is constant directivity. In fact, if you want, while I have these playing, go over to the side, because they all are equidistant from an observer on the side. And stand up and listen to it and put your head down the floor. It gets louder as you go down because of this effect. Now, Now, from a psychoacoustic standpoint, what that means or whether it's good or bad, I don't know. That's for the listener to determine. And again, it's it qualifies as a wideband. And this are just some other pictures of it, with me standing next to it. Now these, there's a lot of drivers and a lot of wiring, and we did it with PC boards, and there's a lot of guts in there. Now one interesting thing that we did, a set of measurements, was comparing this specific speaker versus a three-way high-end system, the Rebel Salon. And Rebel is one of the Harman companies, and this is qualifies as a true high-end speaker, expensive, and it's a very good system. But in comparison to, well, actually it's a four-way. But it represents a conventional speaker, with the driver spread out over the front. Now what I did was we measured this over, both with and without a carpet, over a tiled floor. And basically what we did was raise the microphone up from the floor in half-meter increments, going from the floor up to 2 meters above the speaker, and then measured it at different distances in front of the speaker. And this shows, if you're going to listen to this standing directly in front of it, it's not going to do too well, because if you're near the tweeter, it's going to be high-end heavy. If you lower your head down in front of the mid-ranges, it's going to sound very mid-rangey. And this illustrates that. The only curve here that sort of might qualify is the green curve, which is sort of in front of the tweeter. So you wouldn't expect this. Typically, these kinds of speakers, you have to move far enough away so that the output of all the drivers coalesces. And it also shows, here it is at 1 meter away, and you can see that most of the curves have a big dip around 2 kilohertz, and that's the ground balance. And this is over a perfectly reflective ground plane. Typically, you don't listen to them that way, though. You have carpeting. You try to suppress those. And it gets better as you get farther away. And there's 3 meters. Here, on the average, at 0, it doesn't look too bad, but still you have a lot of rich activity because of the reflections from the ground. Now, conversely, these are this system. The actual measurements on these without EQ. And this is standing directly in front of the speaker, raising the microphone from the floor up 2 meters high above. I mean, it's not that bad, with the exception of the 2 meter one, which is way above. They're not bad. I mean, it doesn't change a whole lot. That's what's significant. And it gets better as you get farther away. And there's no evidence of any floor bounce or deleterious or interference from the floor. In fact, indeed, at 3 meters away, it's very good. So you compare that one with that one. So this has an extremely uniform coverage. Now, one other comparison which you can make is the magnitude phase characteristics. And what I did is I put the microphone 1 meter high, 2 meters away, which is roughly on axis of the tweeter in the Rebel Salon, and measured magnitude phase with a wide 100 millisecond time window, which includes the first floor reflection. And the CBT45 is essentially a one-way system. I mean, there's just one driver there, basically, a bunch of the same drivers. So it's essentially a minimum phase, with the magnitude characteristic is not too bad. But over on this side, I mean, you end up with ground floor bounce effects, comb filtering, but also look at the phase curve at the same point. I aligned the phase with the arrival at the tweeter. You know, there's several rotations, so it's not a minimum phase system for sure.
Is some of that happening at the crossover frequency? Are they actually flipping the phase of the drivers to get the crossover in phase?
I don't know much of the details of the crossover there. You know, Jim Teal, who just recently died, you know, he had, you know, finely tuned arrays done with first order crossovers, which he paid attention to the so-called, you know, the wave shape preservation was very important to him. But with the complex crossover where the drivers had a lot of overlap and everything, but so you what? It's what?
The Rebel had 4-pole crossovers.
Okay. Now this is going off axis horizontally, and I varied the mic position from 0 out to 75 at 1 meter high. And this is what that system looks like at 1 meter off axis over the ground plane.
Gets better.
Yeah, no, that's true. But what the point is on these is for the most part, you know, the response that you measure at one point is pretty much the same as where it is everywhere else. So if you try to equalize it, you're equalizing them all. And so for whatever that's worth. Now this is rather surprising. This is a loudspeaker array, but the center of the array are down on the floor level. I mean, on axis is actually grazing the floor on these arrays. They're ground plane. So when you're listening to these, you're listening off axis all the time, unless you're laying down on the floor. But the vertical polar pattern on these is so dead uniform that when you at an offset listening distance, as you walk near and far from the array, as you get closer to the array, you're off axis, and as you walk farther away, you're more on axis. And that compensates for the near-far variation of sound pressure. And on this, if you plot the sound pressure at seated height, which is about 40 inches roughly, you get a series of curves. This is plotting a series of measurements at 0 meters out to 3 meters in steps of a half a meter, going from roughly directly in front of the system out to 10 feet at seated height. Now all these look very uniform, which is great, but there's a variation here and something on the order of, I'd say 12 dB, near far. So it's less loud farther away. Now, but if you replot it at standing height, surprisingly, this is a family of curves which is very much the same from directly in front of it to 3 meters apart. And you can actually hear this. If you're 10 feet from these and you walk up to it, it doesn't get any louder. It's opposite to what you think. There's no subwoofer there. Well, I weren't. Getting back to these, this is a 100 millisecond time window, so that is the raw response. I didn't have any. Now these have high passes at 150 hertz. You know, if I play them tonight, so it just didn't go down that far. I mean, that's what you get. Now the other thing is, this is even up close to this system. Now here's how I'm varying the microphone position from 1.248 inches away at 1 meter high, which is seated height. And it's extremely uniform right up near the system. Now, earlier tonight, we got the real-time analyzer going with the microphone. I mean, you can put it down on the ground and you can raise it up, or you can go within just 2 or 3 inches of the front of the radiators, and it's just as flat there as it is farther away. So, I mean, if you wanted to think about it, this would make a perfect near-field monitor because it's very good up close to it, if that's worth anything to you. Yeah, right. Yeah, right. Yeah, 48 of them. I'm getting close to the end here, so. There are a number of professional sound systems which you could use to implement these. And I went on the internet to ProSound. I think it's ProSound News, called the ProSound Web, and there are a number of systems, all of which are intended to operate in line arrays that you could use for professional applications. Bunches of them. This is the big thing now, is line arrays and pro applications. This is a new JBL product in their Vertex series. And it's called the VT4886. Now physically this may look like one of those big gigantic concert systems, but it's not very big at all. And here I'm holding one of these boxes. I mean, it's not very big. I mean, it weighs about 40 pounds. So this is not all that big. So this is, JBL has paid close attention to trying to create a seamless high frequency radiator so that you can put these side by side and still have a fairly continuous. I was thinking about some possibilities of doing a ground plane version of this. This thing might cost $50,000, but it would be louder than crap. Yeah, no, yeah, it's
We're talking heaters here.
yeah, right. And they have a special cardioid sub. I mean, it's a sub. But no, I'm sorry. There's several drivers inside these base boxes, and they use them in 3 and have the center ones face to the back, so you can get a cardioid response. You know, to get real, true directivity down at low frequencies. So here I just thought about making 6 per side.
If you have 48 of those, it wouldn't be a cardioid, it'd be a cardiac.
Yeah, there you go. How many what?
How many watts to horsepower?
750? Yeah.
They got 19 kilowatts.
It's funny, you think of all the drivers here, but you're really talking about twice that many because there's the ones down below the ground level.
And it's way less than a ton.
Well, I don't know how, well, yeah, well, this is heavy. That's the LF, I think.
Question?
Yes.
Wouldn't you rather than have them hanging from the ceiling than on the ground to avoid?
Well, there is, that's something that Floyd Toole talked about as an application of this in a home theater where you took the ground plane unit and put it upside down on the ceiling.
Yeah, I mean, I've been at outdoor concerts where you sit up and you hear the full frequency, or stand up, you hear the full frequency range. You sit down and it's like you turn the treble control down 15 decibels.
Okay. Well, the advantage of this is it would just turn down the whole range rather than just the treble. So but this would be an application of something where you did not have the luxury of flying up above. My son works he's a lead audio tech at Marriott down in Orlando, and there's 3 big Marriott properties down there. And when he does the concerts in the very large, where they have a convention or something, if he can put speakers on the floor, he wants to do that because as soon as you have to hoist them up to the ceiling, you get the unions involved, on the safety issues and everything. So it would be nice if you could set this on the floor and blow people's ears off rather than having to hoist it up in the air, if you wanted to do that. Now here Harman JBL has trademarked the CBT moniker, or the 3-letter designation, whatever you want to call it. And what they have trademarked, it's not a registered trademark. There is a chemical company that has a registered trademark of CBT. But in the loudspeaker industry, JBL Harman has trademarked CBT. And there it stands for constant beamwidth technology. That's what they've chosen to make it, rather than constant beamwidth transducer. So it's the same letters. And they have actually 3 new CBT systems in their lineup, and it's intended for smaller vocal applications. I mean, meaning that the constant directivity is mainly in the vocal range, above 800 or 1,000 hertz. And there are 3. The 50 LA system has 8. It's not. Well, there it is, right there. It has 8 of these special 2-inch high efficiency, high power drivers, and the 100 LA has 16 of these, and I think this is about 1 meter high, if I'm not mistaken. And the CBT 70J is another system in the line, which actually has some smaller tweeters on the front. But these, even though this is straight, this looks like a straight axis one. It's actually a delayed. I mean, the arc is created with delay passively, though. I mean, I don't know too much of the details of it, but it's done inside the crossover with LC all-pass networks or something. And that's a topic of, that's a patented topic that they've applied a patent for. And again, I mean, these systems, and what I've been talking about is a topic of 2 pending patents. So, Marshall Kay is sitting right here in the front, and he founded the loudspeaker manufacturer called Audio Artistry. And one of the people that he has working for him as I guess as a consultant is Siegfried Lindquist.
Yeah, not anymore, but he used to.
Okay, I didn't know that. And he has a number of designs that Siegfried and Marshall worked on, one of which called the Beethoven. Now, this is a current product?
We can still make it. We have not been active building it recently, but we can still make it.
Okay. But Siegfried is very smart, and he knows about the constant directivity and everything also, and his systems are. But explain about this system. Is it
It's a dipole from bottom all the way to the top. There's 4 12-inch subwoofers in the cabinet sitting more to the front.
Okay, 4 12-inch subwoofers. All right.
And then the panel has 2 10s and then 2 8s and a tweeter, and it's dipole up to 1450 hertz where it crosses into the tweeter and it becomes a monopole there.
Okay.
But the dipole action doesn't work too well.
Turn the lights down in here a little bit. Let's see, where are the lights? I think they're around the corner there. You can see that. Please. These are a little dark. Everything that I've had. Yeah, that's better. I should have done that anyways. But these are approximately 13 feet high.
Yes.
And he has 3 of these in his church in a left, center, right configuration. And here they were hanging them. And apparently, I think this was a couple of years ago when you hung them.
Yeah, about 2 years ago.
2 years ago. And they're composed of a series of ribbons. What?
That's the Neo 2.0 ribbon, and then that little driver, the truncated driver you see the Parks Express carries these days, was actually created for us for this speaker. We called them. They didn't have a truncated frame driver. We called them and asked them if they could do that for us. They sent us a couple prototypes.
I mean, so to eliminate the spaces in between
the spacing, to try to get that, because there was a anytime you try to do one of these speakers, you want to get those speakers as close together as possible so they won't start getting chaotic response. And so we were trying to squeeze that spacing as tight as possible. And so we needed a truncated frame speaker that wasn't too costly, and they were able to do one for us under $20 per driver.
And how many of the ribbons are there?
There's 22 ribbons in each.
Okay.
Each speaker. So.
And they, from top to bottom, how many of the other direct radiator driver are there?
There's 28 in each column.
Okay, paired up.
Paired up, right. And we did pairs. We want to make sure we have enough sound pressure level capability at low frequencies, and for any event that we might want to do.
And how far down do you use them?
We're running them down to about 80 hertz.
Okay, so you have subs in there somewhere too then?
We have subs with 16, 15-inch drivers.
Okay, where are those when you have it?
Subs are in the center, in the
I mean, right next to the center, the C.
The CBT, there's a sub on each side of it, with eight 15-inch drivers on each side.
Okay, but in the center, but the center one only though.
There's only a center sub. That's correct.
Okay, I see. There's another view of it.
There's the subs right there. You can see them on the other side.
Where? Oh, here.
Yeah.
Okay.
So who did you say makes those ribbons?
The ribbons are, there's one here that appears, they're made by Fontaine, I think it is.
Oh, okay.
We struggled with this because they were only rated about 20 watts. And I had great concerns that we would blow them out. And, but so far they're holding up. We had
this one, I presume.
That's it. We had a Christian rock concert in our church here a few months ago, and they hit 122 dB in the sound booth. And so, and they didn't blow out, so I think we're going to be okay.
Well, one comment that Marshall made to me was the fact that the off-axis attenuation, I mean, it's so uniform vertically, and the level just drops like crazy after you get out of the main beam width, so that there's hardly any, there's not much coverage where the person stands with his microphone in the front, and it fools you because it's really loud, not underneath, if you know what I mean, right?
Our pastor had a great deal of trouble getting used to this effect because he was used to hearing himself very loud, and he used to tell us, turn it up, people can't hear me. But it was extremely loud out in the auditorium, and on the stage it was very low. In fact, it's so amazing that as you walk down the front of the church, this is the front row, and here the beam just skims the top of this chair. When you walk out from underneath that, you can talk comfortably, and you walk back over here, and it's very loud. It's amazing. The technology, this technology works so incredibly good, and the mathematics, the design you do, and then the measurements you make, they match up so nicely. It's just
You're a good JBL salesman here, so. Now you also made some half-height arrays that you use for.
That's correct. This is the assembly. That's the main array right there.
This is the main array. Okay.
We did that. We made it in two parts so we could bolt it together because it was too big to manage as one unit. So it's basically it divides in the middle and they're bolted together.
What was the total weight of the total array that you were hosting up?
Each array was about 500 pounds.
Okay, well that's.
How many of the ribbon tweeters on each one of those?
22.
Well, I mean, so this is an example of a pro sound system done with not necessarily pro sound speakers, if you know what I mean.
And cost-wise, I priced out different arrays to try and get a good price for the church I go to, and so we priced out getting SOS, JBL, and different arrays, and the cost of one array was more than what we did the entire system for, including the amplifiers.
Huh.
It was about $16,000. We did all three of these, well, actually all 6 arrays, all the amplification and all the crossovers.
Yeah, without using the prepackaged systems like I was showing up there previously. Yeah.
Right.
Okay.
Those expensive JBL.
Right.
So you have left, right, and center, three speakers there.
That's correct.
None in the rear, nothing surround.
There's one of the smaller arrays hanging. That is a monitor array for the stage. There's 3 of those for the stage.
Was that half the radius, not the radius of curvature, the arc angle?
That arc angle, I forget right off the top of my head what it is. I think it's close to 55 degrees.
Okay, so it wasn't too far off of it was just a smaller version of your bigger array.
Yeah, I was just trying to make sure I hit the whole
Okay.
whole stage array.
This is a side view of his church, but this is actually a side view. She supplied an AutoCAD file to me here about a month ago. And this shows the array itself. And it is roughly 11 feet wide with a 77-degree arc angle. And has a 9-foot radius of curvature. And this is where it's oriented. And currently, this is the way he has it aimed.
Where's the monitor array?
Yeah, good question. I don't even know that.
It's not shown, but there are three of them hanging essentially from this point right here and curving down to here.
And where are they
they're
aimed?
designed to fit right in here.
Where are they aimed? I mean, here at the...
They're tilted at a pretty steep angle,
Mhm.
and so the center of the beam is roughly right here, and then it drops off back this way, and then if you get to the front of the stage, you don't hear that speaker anymore, and if you get, it's about head height, it starts to drop off here. When you're standing up on the back of this riser.
If you turn the monitors off, are you able to do far field miking?
In terms of like a choir?
Yeah, or anybody. I mean, let's just say you had some, I know bluegrass guys don't like, some bluegrass guys anyway, don't like contact pickups and stuff
Right.
like that. And you get this really expensive mic and you far field mic. But if you have if you have a lot of volume coming back from the house sound, that doesn't work so good.
Well,
and you're saying you don't get a lot of volume coming back from the house.
no,
Right,
the back wall is entirely absorptive. We put a treatment into the back wall so
I'm
that
just saying, do you do far field miking? Have you tried to do far field miking?
I mean, like of the choir or something, you mean?
Or
Yeah.
an individual without contact.
When we mic the choir, we get more gain than we can use.
Okay, then you do far field miking.
Yeah.
All right,
You
with
can-
like two mics or something?
You can see the stage mics hanging.
What's that?
In some of the pictures, you can see mics hanging over the stage.
Those are already used. The choir's been rearranged now, and so it's in the center, and there's mics on stands that go up just above.
Oh, I see. There you're talking about that.
Yeah. Oh, that's not a mic. That's a speaker cable or something.
Okay.
Go back. There they were. Right over here. There was microphones hanging over here, and you again on those we would get more gain than we needed with the choir.
What town in North Carolina?
It's in Cary, North Carolina.
Which I assume is near Raleigh.
That's right.
Yeah.
The suburb.
Yeah, it is just funny. Marshall emailed me and was making some comments, and particularly says, "I'm amazed at how quickly the level drops as you pass by the 60 dB down point."
Can you say what church that is in case any of us wants to make an audio pilgrimage?
It's Cary Church of God. It's a
Cary.
very upbeat kind of.
Carey?
Cary.
Oh, Cary. Okay. And you have contemporary services there?
Contemporary services.
Okay. Now this was quite interesting. He pointed out in this email that with this system playing, you could walk out the sanctuary and it didn't sound all that bad on the other side of the door. I'm kind of paraphrasing what you told me.
The out of the room test that probably many of you are familiar with is very amazing on this system because you go to a concert and you go outside and you hear the boom, 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 boom. You don't hear much high. You walk out of the room on this system and the intelligibility is still good. The balance of the sound is still good. It's really incredible. And I've heard a lot of concert systems. You can always tell, a speaker is playing because you hear that low frequency rumble going on and you miss all the high end. Well, it doesn't happen that way.
And that's because it's constant directivity, flat energy. No, he commented that having worked with Siegfried Lenkwitz with his dipoles, the out-of-room test is always one he checks, and was happy to find that the balance was amazingly good with these systems. Yes.
Question about using the geometric curve versus the real-world curve versus delay. With delay, you're going to get constant beam width out to the sides.
Absolutely, yes. With the real curve, you're not.
Right. So when do you think it becomes advantageous to go to the extra trouble to use the delay rather than the curve?
I think that's kind of up in the air. We're just going to have to find out by experimenting with them. Yes.
Don, you might want to have Wes talk about why he decided to use the delay on those other speakers.
Alvin Foster has some CBT variant speakers, but one of them, which is in the back here, and this is a freestanding CBT, the one that's back against the wall. And it looks like it has 11 coaxes in it. And it's a straight line CBT with delay creating an arc, except above 2 or 3 kilohertz, it's just the center coax operating with its tweeter. So it's a CBT array, you know, from mid down to low frequencies for the most part. So that's yet another. And that was, we didn't get time to listen to these when we were there. We didn't have time to look it up. But he has a pair of these up on his. Are those are surround speakers? Yeah. You're using them as surround speakers.
Who made them? Leslie Woods designed them, and J.D. Tanner. J.D. Tanner put them together.
Okay. Yes.
So here's an interesting question. If you do a straight line array with the time alignment to
time delay
to shade the amplitude, do you get improved vertical off-axis performance? Because now the thing is looking curved the same, you know.
Yes, that alpha. Yes, you're absolutely right. Now whether right, it has the same. The horizontal coverage isn't a function of position.
There is a cost element. Because the amplification and the DSP cost well a year $50 to $125 per driver, at least for the kind of standards I'm thinking of. That particular one there is about $85 or $90 per driver. So it adds up.
Yeah.
On the other hand, I look at the work that Marshall's brother did, all that wiring, that's not trivial trade-offs.
But if I look out in the industry, you know, there's several companies now making speakers that you can steer, you know, by programming, and you can steer the arrays that have individual amplifiers and signal processing for each of the drivers in a range
Right.
of 16
Yes.
drivers. So I mean, there are people already setting up configurations.
Absolutely.
They
Yes.
chose, you know, to shoot for this constant beam width.
That could be an advantage. Yes. Yeah. Right. Same thing. Right.
Steering antennas where there's no moving parts at all. Just
Right.
Same principle.
It's not a coincidence that my first job was as an antenna designer.
So us loudspeaker types are rediscovering all of this stuff that the RF guys knew 50 years ago.
Well, except RF, you're not trying to get a pattern over 3 decades.
No. That's a very good point. Yeah. These are truly wide band. Monty K is Marshall's younger brother, and he has a world-class home theater. And you can go, he has mfk-projects.com. You can go visit his website. It's neat. He does a lot of really good work on his website. But this is his home theater looking towards the screen and away from the screen. And he has these large line arrays that lined up behind these curtains on the side. In this particular situation, he has this is the center channel, and now he's switched this over to using a curved arc center channel. And this is the top view with the screen and everything. And he's.
And I might point out that center channel speaker that he's currently is based on another paper from Don.
Okay, good point.
That's the crossover.
Yes, and that also works very good. So. I co-authored a paper with Ulrich Orbach from JBL, actually Harman. Now here he has a design for a 120-degree arc CBT, and it's interesting because if you consider where the sound appears to be coming from, that's a problem here because you'd like the sound to appear to come from the center of the speaker. I'm sorry, center of the screen. So if you can imagine a 180-degree arc here, and the center of the arc would be exactly in the center of the screen. But that ended up basically sticking out a bit too far. And he chose a 120-degree arc, which is the actual radius center of curvature is back here. So there's minimal area, minimal error, from people. Of course, it sounds fine for centrally located listeners, but there's going to be more of an error as you go off, but it's not much.
Question?
Yes?
That's below the screen, though, as it shows. Wouldn't it be better above the screen to get less audience absorption?
Yeah, that's one debate that they're having now.
We had that debate, and partly because of the football shape pattern, we decided to put it below the screen because the beam just skims the tops of their heads, and from at least on drawing on paper, it looks like it's going to work better, and that's where he's implemented it right now. One other comment about this point of origin of the sound. Monty came up with a good analogy that I had never thought about. But when you walk around that speaker, it's as though the sound follows you. Have you ever seen one of those paintings?
Yeah.
You walk around, the eyes follow you. It's like the sound follows you as you walk around it, and it's always coming towards you. So.
Yeah. Okay. Good point. And here are some. And this is the Tang band tweeter that they bought from Parts Express. Very small. But what's the outside diameter of this? It's pretty small. 3/4 of an inch or something?
That diameter is about a half inch.
Oh, a half inch. Okay. You didn't bring any of those here, did you?
Unfortunately, I didn't have any in North Carolina.
So, I mean, you can't even see the tweeters are around here. Not there, but here. What's that?
What's the bandwidth of that?
You're going to...
That tweeter is, we've got a resonance frequency, I think, up around 3K or something, and it's the only disadvantage, Tang band is hit and miss sometimes. They make some good products, and this is a nice product. I wish they would refine it a little bit more, but we found a lot of, consistency problems with them. But so we would just go manually change them out. So we got them all to be roughly the same.
So it's a real tweeter, so 13 times the curve. So.
Pardon?
It's a real tweeter, so it's not a wide band.
No, it's not a wide band. It's a tweeter. It probably is really useful from about 4 kilohertz up. And I think that's where he's crossing it, about 4K.
These are just different views. Lots of wires, lots of drivers. Yes?
I think some of us listening-oriented people are feeling like we're losing our listening time.
Okay.
Just so you know.
Okay.
It's getting real late.
Okay, I'm just about there. There's Monty. There's Marshall. I attended I ran the bridge-to-bridge 12K run on October 2008, and they had an outside band set up, and I was considering what possible applications of ground plane CBTs here. So I'm not going to go. I'm just going to skip forward here. I'm not going to say much about this. I'm not. But one advantage, this I am going to. If you look at the roll-off of, this happens to be a 3-meter high, 20-degree arc ground plane array with a 15-degree up above ground beam width. And this is the sound pressure roll-off as a function of distance, and it's pretty much independent of frequency. So it's essentially follows the 3 dB per doubling of distance, out to something on the order of 100 feet or thereabouts. So there's two ways of looking at this. You could, for the same sound pressure up on the stage, you could get 20 dB higher level in the back as compared to a point source. Or for the same level at 100 feet, it has 20 dB less sound pressure on stage. So, I mean, you can take advantage of that. This is Floyd Toole's book where he has, I'm very close to the end here. These are pages from his book where this is based on these sound fields that I have. In fact, these I think are 1 kilohertz, but a point source, a uniform line, a curved line with and without, a curved line, and then he's plotting the directivity, etc. And he's talked about a perfect surround speaker where you put one of these upside down up against the ceiling. And this is a possible application of that for PA use from real long room. So that's it. I'm about talked out anyways here.
Okay, Don, I'd like to present you with this plaque from the Boston Audio Society. It essentially says, thank you very much for coming to Boston and sharing your ideas with us. And you will get a 1-year subscription to the Boston Audio Society newsletter.
Oh, wow.
Thank you
Okay.
very much.
Thank you.